So the general idea is that we're going to have a table. It's going to be a three-dimensional table, of every k value, so of every subgraph, partitioned by the u and v. So if we imagine, given u and v values, we're going to have something like this for k equals 0. For each u and v combination, you're going to have, either 0, you're going to have either the weight of uv, right, in each cell. This is going to be zeros. You have either the weight of uv or infinity for all cells, right? So each cell, and then as you progressively grow your k value, so if you consider k equals 1, right? And this is sort of what I wanted you guys to visualize last class, was the idea that at k equals 1, we still keep our k equals 0 around, right? So k equals 1, we use these values to generate, you use the k equals values to generate the k equals 1 values in our algorithm. So I'm just going to throw up the loose algorithm here, and we can sort of discuss the space considerations. So it's almost the same, except that we start with our k values. So I forget what we called it last class. Was it iter opt paths, perhaps? Opt p, probably. And it's, for k, and for probably u first. And then this is where we do our decision cases, where we assign our values. Yeah. So in here we just say, yeah. Okay, so. So you just say if your a value for k minus 1, given a u, v, is less than some a value given your previous table. So, looking backwards. Plus the same a for, so this is from u to k. Then, this is if. Then, so you assign your k value. Just this. So, does this part make sense to people? Because this is kind of the important bit here. So the general idea is that when we're filling in this table here at k equals 1, we're going to look back in our previous table. So at time 1, this is really trivial. Say we're dealing with, we're dealing with, say, this value here. This is k, or say k is. Helps to give these numbers. So the the distance from any node to the same node is 0. Say the distance so far from 3 to 2 is infinity. When we're trying to fill in, say, the value for, you can give these actual distance values. So let's say 3 and it's directed to. Anyway, the point of the matter is that given a cell here that we're iterating through, so we're in this loop and we've entered into k equals 2, let's say, and we're looking back at 1. So maybe it could even be the first iteration. So after initialization, so we're just going through the first time k equals 1, and we're going to look at our 1, 1 cell here. The value, given this subgraph here is trivial. It's just 0.
Shouldn't that be greater than? If what you had before is greater than what you found.
Yeah, it's greater than. Thanks. And then, so the general idea is greater than you reassign it. So what you're looking for are 2 paths. Like when you go through this matrix, if you find another way to get to the current node faster through U and V, so through the combination of, say, 2 and 3, so 1, 2, 3, that you'll populate this number. So you'll update it. Yeah, does that make sense? And and then when you get to k equals, k equals 2, you're gonna have a whole new set of data, and you're gonna consider this one back there to populate this. So as you go forward in time, you're always gonna get k considering k minus 1. And this is where we were last time, where we were broadly sort of talking about the algorithm. And I guess I posed the question to you, do you see a chance for optimization here? Okay. Do you guys see anything weird about this, or anything that we can do if we're building these tables, and as we're building them?
Just keep the last one.
Yeah, you can just keep the last one, because we're only ever, in the algorithm, we're only ever looking at k minus 1. So as we complete these 2 inner loops, on completion of the inner loops, and we enter the main loop again, so we enter our k loop, we no longer need to consider the k minus 2 values ever again. So the idea that you would keep this around is redundant. And it's actually, this algorithm is theta n3, n3 for space. So it turns out you can actually save space. And so I'm just going to write up a version where you actually achieve those space savings, and it's really simple. So a better version small, let's say. For the initialization, I don't really want to rewrite it, but the general idea is you don't initialize, you only initialize the k equals 0, so you just leave out the k index, and you actually initialize an A matrix of just size of n by n. So it'll be just initialize one of these guys, and you put in the same values as you normally would for k equals 0, and that's it. And you notice in the first algorithm, since the first index is 0, you're not actually initializing k equals 1 or k equals 2. You leave that up to the operation of your algorithm as you're going through the k values to progressively build those tables. So a simplified version is very, very direct. You just say for all the u's from 1 to n. All we do is do the same update. So you, yeah, if it's greater than the current in-between node you're considering.
We got an out of position on K.
No, we didn't, no, we're not using K anymore.
Right.
Oh, no, we still need K,
Yeah.
you're right, no, we still need K.
Yeah.
Sorry, you're completely right. Thank you. We don't store the K values, that's the clincher. Yeah. This is obviously KB. And it should be, I think at this point, we should do still the K minus ones. So, you know, if not, it's an off by one error, it's not the end of the world, but. So we can save a considerable amount of space doing that. Does that sort of make sense that you save all that space? So right now, instead of having a set of many tables we're dealing with, now we just have one. And so what happens is, you know, say we for all the U's and all the V's, so we'll just fly through the table, and by the time we finish, you know, by the time we finish, it's time to start again. And at this point, at completion of the table, you're only ever, like, as you're going through the cells, you're only ever considering relevant past cells. So you don't have to worry about updating values over top of other values, if that makes sense. Like, you're not updating in the future, you're only ever updating values based on a path for the future. So you're kind of safe there. And this A value then is the optimum cost of all your UV paths, and it's a very, very, very simple algorithm. Yeah. So, let's see how we're doing here. So the next natural sort of consideration is that we might want to reconstruct the path. And I think I hinted to it last time. Do you guys remember, like, do you remember what we did for matrix chain multiplication? How we kept track of, does anybody have any ideas of what you might be able to do to keep track of the optimal path as we're going? So the general thing we're doing, every time we do this, we're always finding, every time we complete one of these loops, we're always finding the best K, the best intermediate node. So if that makes sense, if we're finding the best intermediate node, the best given a set from, you know, we're always doing this concept that we have this set of candidates, right? And it's always 1 to K minus 1. So we're always trying to find the best intermediate path here, or the best intermediate node as we construct a path. So we think, broadly speaking, about constructing a path. If we have perhaps an optimal path we're building towards in a network. So sketch one out. So say the optimal path, we know beforehand it's this. And the goal is over here. This is our V, this is our U. So we know, because we're really smart, that this is the optimal path. The question is, given these unexplored nodes, how do we get there? So what we're going to do is, maybe if we imagine we have a time index or a K index, and K at time 1 is equal to this, this can be 1, 2, 3, 4, 5, and 6. So imagine as we're building our K, at first we're just considering a first node. It's very unclear how to get there. The current weight will still be infinity. If we step forward in time, now we're going to start considering, I kind of skipped one. We'll call this 3, just to be terrible. Once we get to you know, as we consider 1, at this point, our weight, our A value will be infinity, right? So our A value at K equals 1, we'll just say equals infinity, right? If we get to K equals 2, I guess the caveat here is that the b has to be, it's going to be infinity to the last x. This is a bit of a weird example. We should make our k node maybe like this guy, or our b node. So, we can add, not just, you know, a simpler example is a triangle, and it's very clear. So let's just do that right here. Instead of a giant path. So 1, 2, 3. We haven't discovered, there can be an edge here with weight 1, 1, and 2. And the point is, after one iteration of the algorithm, our A, we're not going to work with the k value, our AUV after, for k equals 1 will simply be, will be 2. Does that sort of make sense? After we take one step forward in time, say our k set at time 1, if we had it as a set at 1, would just be, vertex 1. The k set at time 2, and just to rejig things, let's just order this so it's advantageous. Our k set at time 2 will still be 2, so it's fine. But our set would grow from 1 to 2. We go through all the combinations and we find, given all the k's that we currently know about, that the best path is still this one, after considering these two nodes. And as soon as we hit k equals 3, then the k minus 1 set can consider all the previous nodes, or as soon as it actually equals 4. So we'll jump right to k equals 4. We're done our set, and we're at the maximum. So say there's some other node. That's not relevant either. Our UV, as soon as we consider all the in-between nodes in k minus 1, we'll realize that this cost and this cost collapse this value. Right? Oh, and this is also valued as still 2, so it's not lesser. And that's the crux of the algorithm in a nutshell. So given this example, given that we just did, can you think of a way that you could reconstruct that path as you're building your network? So one way, so let's think about reconstruction. Our algorithm does two things. One, nothing. Right? It just leaves a UV alone. So what do we know about path reconstruction in the case that you don't update anything? It's already the best plan. So already the best plan. So if we consider having some, B value, reusing the same notation from the matrix train multiplication, we can say that the BUV value is going to be the same. The question is, when we do an update, we found a better path. And which node did we find a better path through if we're updating the value? The k value, yeah. So that at that point, if we found a better path, a better path is found, we can simply assign our BUV values the value of k. And so what I'd like to write up now is a version of the algorithm that does exactly that. That as you're going through, it doesn't change anything unless it finds a better path. And when you do find a better path, you just store the node that helps you find that better path along the way. It's a pretty, and it turns out that what you're actually doing is, since you're always looking, you'll always end up storing the maximum k in the set from 1 to k that helps you get to that value. Because your k value increments in the parent loop of the whole application. K value is incrementing up here. So this global K that you're currently working with will be the one that you'll track as the intermediate node that you care about. If that makes sense. Yeah. Okay, backtracking. It's similar to the predecessor matrix or predecessor path in George Joyce. So the general idea is that yeah, okay. So again, we have to initialize for all the U's and for all the V's. This is initialized. Yeah. Our UVs, sorry, if the U equals the V, we're going to assign a UV 0. Yeah. If the pair UV is in the set of edges, yeah. So we just don't want to care about self connections. Not very useful. Yep, okay. So if there's a one-step link, and is minus 1 as well. Okay, cool. So these are just uninitialized. And that's the general initialization technique. The loop is exactly this loop, so we're just going to augment it with our B value. So it's fine to rewrite it. Oh wait, it's not this loop. It's the one, that guy. So we're just going to augment this. So we keep updating when the optimal sort of intermediate path between U and V uses the biggest node K. And it turns out that when you store this two-dimensional matrix, that you end up with a pretty advantageous representation of V values, such that it's possible to reconstruct your path pretty easily. So we'll do that right here. Yeah. So yeah, so my memory for exact formulations of algorithms is not what it should be. Yeah. Return. So this guy should take arguments of 2. Yeah, okay, that makes sense. So here is where we do the cool thing. And I don't know if you see what's sort of going on, but this is the path, this is going to return the sort of recursive path between u and the maximum k that connected u to b. So this is where, you know, if you have these optimal subpaths that you built this path previously, and you remember, you know, say this is your u and b at one point, you remember, oh yeah, that's the k that connected us, right? And then say later on, this is another uv path, you remember, oh, this is the k2 that connected us. And remember for, you know, for the global subpath from the u all the way to the b, that this is the k3 that connected u. So as we work backwards, if we're considering the whole uv path, this will be the first k we get. And then we're going to consider this subpath, that's the second, and then, you know, or second or third, or whatever, these kind of at the same time. And that's how the reconstruction operates. Can you guys visualize that? And that's based on exactly this. So, and then as you recursively work through your path, you're going to get to a point when BUV is not greater than 0, you're going to hit a -1 eventually. You're going to hit the point where, you know, either it's -1 because there's no path, and we never found a connection. So that'll be this case. So if it stayed -1 here, there was never a connection, and you'll never even enter this loop. You'll never even enter this recursive formulation. The other case that's -1 is if you actually hit a terminal node. And then at this point, you can just return. Yeah, just return if it's equal to 0. That's the caveat. So if you get down to BUV equals 0, it means you've hit sort of one of these situations where you have a node 1 connected to a node 2, and you can just return the UV tuple as a pair, because you know it's a 0. It's this case here, and then if everything else fails, you just return empty. So there in fact is no set, and that really only catches. You know, the expected result of the algorithm is that you enter this many times and then end up here for each terminal node. And if you enter in a UV pair that's not reachable, you fall through all the classes and return empty. Yeah. And this would be the case really, you know, where this is the -1 case where you just never found the path at all.
So there's never the possibility that one of the recursions will land us there.
Shouldn't. It shouldn't happen. And I'm going to go on a limb and say it's not possible. Because if U and B are reachable, at some point they're going to get initialized along the way. Because B will be assigned some K value. And the only time it's 0 is when the UVs are adjacent. So the only time it's 0 is when every value, you know, every set we've defined has vertices starting with 1. So the minimum value you can ever have assigned to B is 1. So you're never going to assign a -1 during the operation of the actual pathfinding algorithm. Didn't erase it, did I? Right there. Yeah, you'll never, K, this value is always greater than 1, you know? It's worth saying like K always. And we just know that because of the K values that we're using. We start from 1, we go to n. If you don't assign it, there wasn't a path. And then otherwise, this recursion takes over. Like, I'm not going to do a formal proof, but yeah, it's just something that is, you can take it on faith if you like. So this guy here. So in digital today, what do you guys think? It's strange, right? There is a cool example that we can work through. What do you guys think about this example? The optimal paths example. Okay. I think it's pretty clear. I mean, there is a lengthy example in the notes of going through the paths and reconstructing a path, so it's worth going through. But I think, like, I mean, if you step through the algorithm, it's got a good example of the k values that you can encounter, so I'd recommend going through it. But I think that there's a cooler subject, which is transitive closure. Do you guys know what transitive closure is? Do you know what transitivity is? A is to B is to C. So the general idea, it's called, people call it transitive closure. But the general, the real like sort of English version would be, is there a path from U to B? Like, does that exist? And so the question is there an easy way to answer that question? If I asked you right now, is there a path from U to B? Could you answer that question? And I hope that, and raise your hands if you think that yes, it's easy to find that. Yeah, because we just did the algorithm, so it's actually pretty, we can do it right there. So it turns out that we can execute this algorithm, we can find whether or not a path from U to B exists, and we can do it in, using the this path algorithm, we can find the, in O(n)(3), we can find the solution, and in O2, we can represent it. So the problem is, given an input graph, find all the nodes that are connected. Usually people talk about this as like G star, or they can, given some set E star, where the G star is a special version of the graph, and the E star represents, broadly speaking, the idea that it's all the edges such that they represent the fact that there is a connection between U and B. So each edge, or a path, that the path PUV exists. And this would be given the fact that E equals, UV. So if you have this edge, then we know that a PUV exists, PUV exists in G. So broadly speaking, an example of this might be, given an arbitrary graph that might look like this, for example, with 1, 2, 3, 4. So if this is your G, VE, the transitive closure would be equal to GVE star. These are directed, say. And does anybody want to help me build it? It's pretty, so this is 1, because there is a path. This is obviously a path. It turns out that in this trivial example, the only edge that's added is this one. And so there is an edge, because there is a path from 1 to 4, we get this structure here. The goal is to generate this. And reachability analysis in networks can be really important. Like, I mean, in terms of the internet, it's very important to know whether one node is reachable by another node. And that's, broadly speaking, when we had our good friend in talking about satellites, that was the prime concern of a satellite network is determining the transit closure. And it's actually a problem in many, many network applications. It's also a problem in research, determining which states are reachable by other states, and we'd like to be able to do it efficiently. So do you guys think we should just use our regular algorithm for this? Like, is it good enough, the fact that we're going through O(n) cubed operations? It turns out it's a little bit hard to improve. So it's hard to improve on the shortest path algorithm without getting strange. But broadly speaking, it does a lot of wasteful operations because we're actually calculating the distances. So if we think, I just erased it, but we are doing a couple things that are expensive. Can anybody name something that we're keeping track of in the shortest path algorithm that we actually don't need in terms of determining transitive closure? We already know we have our net -1 values, which is fine. So our -1s in the B's definitely tell us that we don't have a connection. We can run our shortest paths algorithm and we can get all these values. So what do we get from our shortest paths algorithm that we previously liked but now might be a little bit wasteful? The shortest paths. So it turns out that we actually don't care what the length of the shortest path is. We can just simply track whether or not a path exists. So we can change addition into logic. Meaning specifically, we can take the operation where we do A given a previous K value, U, V. Where we can change this operation. Sorry. KB. We can change this. I want to do another big arrow. Into something more of a form. We can use a logical AND. Right? So if we do that, we can save a lot of operations. And if we populate the values as we're going forward, instead of if we initialize them, they're already ones or zeros. So if we initialize them differently, and this is where I should probably, it turns out that it turns out that you can just take the logical AND of these operations in your algorithm, and that will actually work out well. So does that actually follow from the initialization? So what we'd have to do, we'd have to do some work in initialization. Essentially, we just have to change this guy to 1, so that when we logic AND it in the future, it doesn't come through zeros. And the infinity can change to a 0, so that we take an AND with a 0.
The weight would be a 1.
Sorry?
The weight would be a 1 as well.
The weight, and also the weight would be a 1. So if we wanted to, copy the same algorithm for transit closure, some really cool examples for this too. So if they're the same, here, the UVs can become 1. I feel like someone should double check that for me, but if not, I'm pretty sure. So there is a connection there. And lastly here, this becomes And here, like, there's also, so that's sort of number one, but we also have to worry about our condition. So we have a second thing to worry about. Let's do it this way. Does anyone want to tell me the second thing we have to worry about is? The other mathematical operation we're doing in our algorithm? So we have to add the A values. There's one more thing we have to do. That's one logic operation. Replaced. The other operation in the algorithm is when we actually do the conditional check. Right? So all we want to do is we just want to replace this. It's actually even cheaper, right? Because instead of replacing it whenever we find a greater value, we just want to check and replace it when we find a value that isn't already there. So we just want the case where, you know, and I believe it's, I believe that's the AND case. Actually, I think the if statement is the place for the AND, perhaps. Change condition. So we change our if a u v is greater than a k kb. So yeah, we changed this guy to an AND. So essentially we want to check to see if this is 0, and then we want to say, you know, the AND of these two values, then we want to put in, and I think it's actually the or was it the, yeah, let me just see here. I don't have a good example of the algorithm on hand, but the general idea is that you replace them with logical operations. And so we replace this with the condition with I think this is, yeah, I don't know.
Yes.
So between these two, I've reversed a condition. One of them is the if statement. There's an and an or, and I don't know if you guys want to help me sort of. Let's see here.
But you gotta call it max.
Yes.
You don't need the max. You don't care about the max anymore. All you care about.
Like to do the 0, 1, believe it, to see that, you know, the different in existing, the iteration before the.
Yeah. So essentially, what's happening is you're checking beforehand. So let's reason this out.
Yeah.
So you're checking the iteration beforehand, and you're concerned with the situation when the current value equals 0. So really, what you're concerned with is the fact that AUV equals 0. There isn't a connection, and you know that the previous, like you're still going to go through all the K's.
Right.
And then what you want to find out is if A, there is a connection from U to K and from K to B. So if this, so really it's this, then you're just going to assign, you're going to do your previous work.
Yeah.
Then you say A, and I think you can actually just say equals 1. Do you know what I mean?
Yeah, so like what I'm saying is you can say AUV equals the max, AUV, comma, AUK, and AKV.
Yeah, and I actually think that you don't even need to do that, because if you fall into this logical situation,
Yeah.
I think that this is actually it. I think this is overly
Yeah.
complicated,
Yeah.
unnecessary. So there's the idea that you can simplify this operation to an and, but I think in principle, if you just check for your, the previous values and the fact that a path exists, given this connection K, that's sufficient. You can possibly save operations by, and I don't know if they do this in the final version of the algorithm, by making sure you don't do the assignment if you don't need to. Do you know what I mean? Like, because there's no point in redundantly assigning 1, 1, 1, 1, and that might be something that they might have done in the like sort of final version of the algorithm.
But it's still the K minus one.
Yeah, you always look back to K minus 1. Oh yeah, thank you. So you know this would be K minus 1 in here. I can just write out a whole version of the algorithm for you guys if you want, but I think it's the same algorithm, and yeah, we built it together. So yeah, that makes sense. And so this idea that we can find our transitive closure by just, you know, piggybacking on this current example is a general sort of idea in the course, and also, I don't know if you noticed, you know, the first assignment is, what algorithms do we already know that solve this problem, and how do I prove that this problem is in the class of this problem, or this algorithm is, or the problem we're trying to solve can be solved by this algorithm if we just do a tiny change like this. And that's a general sort of problem-solving approach that is really advantageous. You know, and in the first assignment, the idea was, you know, given a greedy algorithm, at what points are you able to recognize, like, okay, I can solve some things that are greedy, but then there's this other bit that doesn't really fit in, and that's when you want to start considering other problem classes, when you can't really shoehorn your problem into a certain size. And you can maybe you can solve part of the problem one way, but not the whole problem, and these are some of the considerations you'll make. Yeah, so after this, how long we should start? There's no point starting anything now. Upcoming though is network flows, which is pretty cool. I'll put the readings on the board for you guys. I feel like I did you guys a disservice today because I had all these really great diagrams built and cool examples written up, and then I left them at my office. I had to bumble through with 100 notes. Yeah, so let's go for readings. Do you guys do the readings? Is that a thing you do? Because the textbook's pretty good. Say what? People what? Before the midterm, yeah. It's not, okay, the lecture notes are not like super hard, so the textbook isn't. It's good to read along with.